Friends, welcome to lecture 63 of Advanced Steel Design, where we are continuing to discuss the procedures for fire resistant design as a part of this course. In the last lecture, we discussed about some essential characteristics of fire, what are the tips for a good fire resistant design buildings, and so on. Now, we will focus more on design methods. For fire resistance. This has got a specific reference to APA RP 2A, American Petroleum Institute recommended practice 2A. This specific quote says there are three possible ways by which you can design fire resistant structures. One is by what is called as a zone method. Two, linear elastic method, and the third one is elastic plastic method. In the zone method, the maximum allowable temperature is assigned to the steel member. This method has no reference to the stress level in the member before fire. Okay. Let us say in a given building there are zones where there is a possibility of fire, let us say this member and let us say this member, column and this beam. These are the possible locations where a fire could outburst. Okay. So, now these steel members are assigned to a maximum allowable temperature up to which it has to sustain. When you do that, you do not have any cross reference to the stress level in these members before fire. Okay. So, the design is more focused on member utilization ratio, the basic allowable stress will remain unchanged. Even under fire. That is, the reduction in stress level due to high temperature is not accounted in the design as the allowable value. Okay. They remain unchanged. So, this method is focusing only on certain areas, on certain members which has got high proximity of fire, probability of fire occurrence is higher. So, that is why this method is called zone method. Okay. In this method, the yield strength sigma y is reduced by a factor of 0.6. Now, there are disadvantages of this method. One, it is not applicable with the unmatched reduction in both sigma y and E, because you have a constant number. Okay? So, this affects the design criteria. The second method is linear elastic method. In this method, the maximum allowable stress is assigned to the steel member based on the stress level before fire. So, here the main focus is to maintain the member utilization ratio. Close to unity. So, effective utilization is ensured, and this is done even at increase in the temperature. Okay. In this design method, the stress level corresponds to the assigned temperature level. So, you have to pick up the yield value with respect to the corresponding temperature level of steel during fire. Okay. So, when you talk about the temperature variation during fire, then you may ask me a question, what temperature should I consider for estimating sigma y from the material property? That is a good question. You can have a maximum temperature, you can have a minimum temperature. So, what we generally consider is your core average temperature is considered and the equivalent sigma y at that temperature is taken for design. Okay. This method has some disadvantages. This method also proposes an unmatched value of sigma y and E, which is a serious concern, because the degradation in Young's modulus and the yield strength are not same at a specific temperature. Okay. It considers an average core temperature value for which sigma y is considered, but E is not accounted with respect to the temperature variation. The third method is elastic plastic method, where the maximum allowable temperature is assigned to the member based on the stress level before fire. Friends, this is not assigned to all the members, it is only assigned to critical members. What do you mean by critical members? The members whose stress level is maximum before fire. Okay. As a result, the member utilization in this design procedure is lesser than 1.0 with the increase in temperature. So, all members are not subjected to uniform stress range, only those critical members subjected to higher temperature during fire is assigned a specific stress value. So, therefore, one need to verify the structure under collapse. Okay. So, you need to verify the structure under collapse loads, but the design should ensure serviceability under fire loads. So, that is the design criteria what this method ensures. This method also has couple of disadvantages. Commonly used strain value in the design is 0.2, which matches with the reduction in sigma y with increase in temperature. Okay. But selection of higher strain will result in higher temperature. See, you are looking for an average temperature for which the strain value may not be 0.2. In the last lecture, we discussed about the strain variation in steel with respect to temperature. So, either you pick up the strain value for a specific temperature or for a specific strain pick up the temperature. So, the procedure says you pick up the stress value for a specific temperature for the critical members, but when it assigned the strain value, it is 0.2. So, a higher strain value assigned to the members will result in higher temperature, which will not match with the stress and Young's modulus for the design. So, that is a concern in this method. Okay. Having said this, let us talk about energy released during fire. If the ignition fluid is present in the building, then the total energy released during fire can be given by what is called as fire load. So, fire load is the total energy which is sum of Mi Ci, where Mi is the mass of combustible materials present in the building in kgs. Ci is the calorific value of each material which is either in joules per kg or of course megajoules per kg. For common materials being used in buildings, National Building Code Part 4 gives the value of Mi and Ci value of different materials. Look at this table which is extracted from the National Building Code for different materials. Let us say solids, hydrocarbons, common solids, even foodstuffs. The calorific value and the wood equivalence is given in the code. Let us do a small example. Let us say there is a presence of 200 kg of benzene hydrocarbon. Okay, if you look at benzene hydrocarbon, the calorific value is 39.6. I can say megajoules per kg, because 10 power 3 I have taken as megajoules. Now, the average release rate which is called as HRR can last for 1 hour. So, we can say E is going to be 200 into 39.6, that is 7920 megajoules. So, the energy released Q can be 7920 divided by 60 into 60, which is 2200 kilowatts. Okay. Let us do one more example. Of a mixed mass. You can see on the screen the NBC table extracted. Let us say the building contains 100 kg of benzene whose C value is 39.6, 50 kg of butane whose C value is 47.1, 200 kg of ethane whose C value is 49.1. So, the average energy released during 1 hour is called as HRR, heat release rate, that is 60 into 60 seconds, is given by sum of MICI, in our case going to be 100 into 39.6 plus 50 into 47.1 plus 200 into 49.1, which comes to 16135 megajoules. So, Q will be 16135 into 10 power 3 by 60 into 60, which will be 4481.9 kilowatts. Okay. Let us look into the T-square fire model, which is a very common time temperature curve, okay, which is being used. It is also called as TT model or a T-square fire model. This can be used to quantify the energy released. Okay. Furthermore, friends, you can also see the time temperature or time heat release rate curve, where the alpha g T square, which is the heat release rate, depends on a factor which is there for different kind of fire. Okay. Let us say if it is a slow fire growth, alpha g is different compared to ultra fast fire growth. Now, if the fire growth rate is known to us, we can estimate the time of burning. We can easily find out how long the fire will be sustained. Okay. Furthermore, there are different phases of fire growth: initiation, growth phase, decay phase and end of compression. So, in the growth phase, there is a significant rise in the heat release rate, which reaches its peak and then it gets decayed, as you see here in the figure. Okay. So, now let us say, for example, I have 100 kg of fuel oil. Fuel oil. Okay. The fuel oil has got C as 41.6 megajoule per kg. From the table. Let us assume an ultra fast fire to take place. Okay. The peak HRR, that is heat release rate, is 9 megawatts. We want to estimate the time of burning. Let us do that. E is 100 into 41.6, which is 4160 megajoule. The growth factor for fire or ultra fast fire, that is alpha g. From this table you can see it is 0.1874, 0.1874 kilowatt per second square. Therefore, the time taken to reach the peak HRR, that is QP, is 9000, because we already said the HRR is about 9 megawatts, divided by 0.1874 root, which will be 219 seconds. Okay. Now, the total energy released in the growth stage, let us call this E1, can be computed as Q by 3, which is 9, Qp into Tp by 3, which is 219 by 3, which is 657 megajoules. Since the 657 megajoule in the growth stage is much lesser than the heat release, which is the energy present because of the oil or because of the fuel oil, okay, we can say the total burning time will be Tb, which is Tp plus 4160 minus 657 by Qp. So, in my case it is going to be Tp plus 4160 minus 657 by 9. Which is about 10.1 minutes. Let us discuss about the time temperature behavior of fire. Friends, there is a significant difference between the real fire and the standard fire. Fire has a starting phase which is initially small, about 20 minutes. So, it is during this time one can activate the firefighting equipments like fire alarms, sprinklers, extinguishers, call to fire station, evacuation plan, etc. All can be activated during this time. Okay. It is always good to provide a compartment design. So, the fire does not spread to the places where devices and equipments are kept. Okay. So, friends, we must understand that firefighting is initiated during the fire growth phase. Okay, during the fire growth phase. Following by this, let us have something called pre-flashover stage. This is true up to a temperature less than 600 degrees Celsius. The post flashover stage is called as the burning stage. Okay. It is interesting, friends, for you to note that hydrocarbon fires which happen in offshore platforms can reach the temperature as high as 1200 degrees Celsius. Okay. Therefore, friends, in such cases, fire reaches its peak temperature approximately within 90 minutes and then starts decaying. Okay. Usually the decay period of fire is about 4 to 6 hours. Okay. But it contains and depends on the unburnt inventory. Okay. Let us look at this curve, which is the pre-flashover and post-flashover stage. The pre-flashover stage is about approximately 20 minutes on initial ignition and smoldering, then the burning takes for 90 minutes, then the decay is about 240 minutes. The natural fire curve is what you see here, okay, whereas the standard fire curve always starts after the pre-flashover stage, okay, after this stage. So, the philosophy for design is that the structural system should not collapse even at high intensity of fire. Okay. There are various codes of practices which ensure this fire safety, which shows the standard fire curve. For example, IS 3809, ISO 834, ASTM E119 helps you by providing the standard fire curve. Furthermore, we can also estimate the fire load energy density. Which is called as flood. Okay. The fire load energy density depends on different code provisions which are also carried and revised by different countries. For example, in London, the mean flood energy density is about 330 megajoules per square meter, whereas in India it is about 348. So, it keeps on varying, and these effects are reflected in the respective national standards of the countries. A recent study carried out by IIT Gandhinagar in 2015 shows that the mean value of fire load energy density is much higher in reality. Okay. This was tested in the laboratory, and people have reported that the FLED value for design, which is referred as different codal provisions, are far lesser than the actual value. Okay. Now, for the standard fire curve, T is given by T0 plus 345 log of 8m plus 1 for the standard fire curve. We will call this equation number 2. Okay. Now, look at this fire curve back again. It says that the natural fire curve has got a cooling phase, is it not? The standard fire curve closes here, whereas the parametric fire curve, which is indicated in Eurocode, which is EN 1992-12, indicates a cooling phase for about short period. Okay. So, now there is a cooling phase which is shown in the red color here. Okay. So, this is for the natural fire, which also indicates a cooling phase, whereas in standard fire curve this cooling phase is missing. Okay. Whereas if you look at the Swedish fire code, in annexure A, FLED is revised based on the room shape and size and openings present in the room and inventory materials present in the room. So, there has been a revision in the Swedish fire code to compute the fire load energy density not as a standard value, but is dependent on realistic parameters as you see here. The standard fire curve only indicates the growth phase, but does not talk about the cooling phase, whereas the parametric fire curve used in Eurocode talks about the cooling phase as well. So, therefore, friends, in fire resistant design, the first step is to compute fire load energy density, okay, which is given by QFD, which is QFK of M del Q1, del Q2 and del N, calls equation number 3, where M is the combustion factor, which is approximately 0.8. Del Q1 is a fire activation risk, which depends on the shape and size. Del Q2 depends on the type of occupancy, and del N is a combined effect of the above factors. Okay. Now, QFD is called the design FLED. QFK is called the characteristic fire load density per area of flow, which will be expressed in megajoules per square meter. Okay. For example, in National Building Code, of Indian practice, it is said as 25 kg per square meter of wood equivalent of wood. Okay. So, we now say wood equivalent, we can say, which is 25 into the calorific value of wood, which is giving me 425 megajoules per square meter. Okay. Now, the other factors del Q1 and del Q2 are given here depending upon the type of occupancy and the size and shape. If the compartment area is about 25 square meters, del Q1 is about 1.1, and for art gallery, museum, etc., it's 0.78, whereas manufacturing fireworks is about 1.66. So, the example of occupancy is also listed here, which helps me to compute the del Q1 del Q2 factors required to compute the FLED of the design value. If we have firefighting systems which is useful for suppressing fire with water extinguisher systems, independent water supply system, fire brigade located off site, or firefighting devices available, then the del N value is also varied. So, it is a combined effect which is useful to compute the FLED for the design. The table what you see on the screen is an average value of QFK in megajoules per square meter. This is QFK. So, for example, QFK for dwelling units is about 948 megajoules per square meter, which is equivalent value of wood. Okay. So, it is available for different kinds of public spaces as well as private spaces, which is used for the design, which is a characteristic value. Okay. Now, with the help of these, one can compute the FLED. Now, the second step involved in fire resistant design or the fire load estimate is heat phase calculation. Theta g is given as 20 plus 1325 times of 1 minus 0.324 E minus 0.2 T star minus 0.204 E minus 1.7 T star minus 0.472 E minus 19 T star. Go to equation number 5, where theta g is expressed as the gas temperature in degrees Celsius, which is based upon the time delay. Okay. T star is expressed in hours. T star depends on opening factors, that is the ventilation, then area of the vertical opening in walls, total area of the compartment for which fire resistant design is attempted. Okay. T star is taken as T gamma, where T is the actual time in hours and gamma is opening factor by breadth B square. Okay, let me write down here. Gamma is opening area by breadth square, which is 0.04 by 1160 square. Okay, let us not. So, gamma is based on the ratio of opening to the whole area. Okay. This is referred as other factors that influence the design. Okay. Now, gamma is O by B square, where O is called as the opening factor, which is AV root H equivalent by A total, where AV is ventilated opening, AT is the total area of enclosure, okay, and O lies between 0.02 to 0.2. H equivalent is the average height of windows in the openings. Okay. In this expression, B depends on the material property. B actually given by rho C lambda for 100 and 2200 joules per square meter per root S K, where rho C lambda or density, specific heat and thermal conductivity of the material. Okay. Rho C lambda product is called thermal inertia. Of the compartment. Gamma, if it is unity, which will refer to the standard time temperature curve. We have seen two curves, right? Standard and actual. This is equation 8. Opening factor also depends on or also governs the fire behavior. In general, all fire are ventilation controlled. Few of them could be fuel controlled. For example, in offshore platforms, you got lot of ventilation around, so there is no problem of ventilation, but inventory of fuel will control the fire. Okay? Fire intensity depends on the fuel. Okay? So, let us say T star max is the maximum value of 0.2 10 power minus 3 Q T alpha by O T limit, where O is the opening area and T limit depends on whether it is fuel control or ventilation control. Equation 9. Now, Q total or Qt of D is Qf of D AF by AT for 50 less than or equal to QTD less than or equal to 1000 megajoules per square meter, where QFD is called the design value for fire load density, which is computed based on the total area of ventilation, which is AT. The third step is the cooling phase. Now, theta G is given as theta max minus 625 of T star minus T star max comma x for T star max is less than 0.5 hours, is equal to theta max minus 250 of 3 minus T star max into T star minus T star max x for 0.5 less than T star max less than 2 hours, where x is given by 1.0 if T star max is greater than T limit it is equal to T limit by T star max if T star max is equal to T limit. Okay. So, friends, in this lecture we learnt about the heat release rate of fire load. We also learnt about the standard fire curve and the cooling phase of the fire curve. We understood the time, temperature, behavior of fire and understood how to compute the fire load for design. Okay. So, more details of this fire resistant design part can be seen in a separate course of NPTEL conducted by IIT Madras by me on offshore structures under special loads including fire resistant design. So, design examples are available, and I also authored a book on fire resistant design which can be useful to you for working out more examples on this. Please refer to them and try to also refer the DNV code and the European code for learning more about the parametric fire curves. Thank you very much and have a good day.